it. Of course, you have your assignment 1 still going, for which you are required to submit your project report on the on the day that has been declared. So today let us just finish our discussion related to how natural language processing and text mining can be used in economics problems, specifically for sentiment analysis. So in the classes of Monday and Thursday, we had discussed several concepts. So first of all, we mentioned about the important components of a natural language, namely first the vocabulary, the grammar, and the semantics. So related to the semantics, we talked about WordNet, which is a resource of the words in the language, like in our case English, which basically contains in a sense it's some kind of a dictionary which contains a list of the different senses of a different word along with their corresponding parts of speech. Now, based on this, we considered the problem of the word sense disambiguation. That is, we have a single word which can have multiple senses, but in a document when a word token appears, so we have already discussed that the occurrence of a word in a document is called a word token. So every word token is linked to a particular word in the vocabulary. Now the word in the vocabulary can have multiple senses, but the word token can have only one sense. And so which sense is the most likely, that is determining that thing is called the problem of word sense disambiguation. And to determine the sense of a particular word, the what we need, or the biggest tool we need, is the context of the word. By context, what I mean by that is the neighboring words. Like if we look at any word token in isolation, we may not be able to understand which sense it is being used. But if we look at the neighboring words, then it might become clear to us which sense is being used. And so for this purpose, we also described an algorithm called a Leske algorithm, in which we consider the wordnet definition of the target word as well as the wordnet definitions of the context words, and we calculate the intersections between these wordnet definitions, and based on that we attach a score, and finally based on that score we are able to solve the WSD problem. Now we came to the problem of sentiment analysis. So once we have identified all the important words or important keywords for which we are looking for, or against which we are looking for the sentiments, the next task is to determine the sentiments. So just like WordNet, we need a resource for knowing the sentiments. So like there are some words which denote sentiments. There is so there, just like WordNet, there is another repository or a resource which we call as the Senti WordNet. So is my screen visible now? Can you see the screen?
Yes, sir.
So in case of Senti WordNet, like we have, like as we had seen yesterday, like there is a list of words. Each word has a positive score and a negative score. The positive score, like both of these scores are a value between 0 and 1. So like if for word 1, the positives and negative scores are 0.1 and 0.6, it means that now these scores can be interpreted, are open to interpretation. These scores do not have any clear mathematical meaning, but you can that is, you can interpret it in the following way, that 10% of the times this word W1 is used in a positive sense, 60% of the time it is used in a negative sense, and the remaining 30% it is used in neutral sense, and so on. So these kinds of scores are attached with all the different words. Now these kinds of now the thing is that these kinds of positive and negative sentiments are usually attached with some words. That is, we cannot really go about like all the words in the dictionary and keep on attaching the positive and negative scores to it. Not that, nor will that have any particular meaning. So, I mean, there are lots of words uh, which are completely neutral, which have nothing, which are neither positive nor negative in any context. For example, if you consider a word like computer, is there any reason to think that the computer, this word, is either a positive or a negative? Certainly not. Like, it's a neutral word. That is, sentiment wise, it's a neutral word. So now the question is, so now the thing is, suppose I want to build, to create this senti wordnet. So what is the way in which I can build this kind of senti wordnet, that is this kind of a resource? So of course, like, it will require people to sit and manually sit and do the tagging, but of course, but there is of course a limit to how much of tagging one can do. That is, you cannot possibly like take like a, that is, you can, that is, it is not possible that you will take some millions of words and or millions of documents and tag each word one by one, whether it's indicative of a positive sentiment or a negative sentiment and so on, right? Now also it, and as we also notice, that it may often happen that a particular word by itself may not be either, may not have either positive sentiment or either negative sentiment, but they are some, they may be, there are certain words may be used in more in a positive context, and some words may be used more in a negative context, right? Even though they are themselves like neutral words. So what do we do with these kinds of words? So the one way to do this task is as follows. Start with some anchor words. Anchor words means what? Some means some words which are definitely positive or definitely negative. Like for example, good or awesome, right? Or terrific, or maybe joyful, etc. And like, these are words which like, which are like almost certain to be used in a positive sense. On the other hand, there can be some words which are like always used in a negative sense, like for example, maybe a bad or horrible, then cursed, etc, etc. So like, that is, we like, we have some understanding of like which words are always used as positive and which words are always used as negative. So let us say that this kind of a set of words is has been developed, which we call as the anchor words. Now we take any arbitrary word w. Okay, and now what we are trying to do is, we are trying to see how that is, so this word w, this is not an anchor word, it may be a neutral word, but they are, as I said earlier, there may be some neutral words which are usually used in positive context, and some other neutral words which are usually used in negative context, even though they themselves are not anything are not indicative of either polarity. So uh, what has to be done is, once we have got the anchor words, next we have to induce the sentiments of these anchor words onto other words. So the like, if you consider any arbitrary word w, the one way of assigning the sentiment to it is as follows. You calculate the following, like what is sometimes called as the as this quantity. This is like, this is an information theoretic term. This is called the mutual information. Okay, now let us say that p is a any positive word. Okay, is a word which is present, which is a positive anchored word. Now what I will calculate is, so it's like saying that what is the probability that both the words P and W appear together in as a context. Now, the concept of context we had discussed earlier. So, like, just to recall that, like, as we all know, that a sentence is nothing but a sequence of word tokens. So, suppose the word W appears in a sentence. So, it will have some words surrounding it in that sentence, or maybe in the surrounding sentences. So, what I can do is, like, I get the set of words, neighboring words, they form as the context of the word W. Maybe M words on this side and M words on this side. So that will be a context of size 2M. Okay. So now what it is, now what this is being said is that like what is the, that is across a very large number of documents, what is the probability that these two words occur together, that is one is in the context of the other, that is either W is in the context of the word P or P is in the context of the word W. This probability divided by their individual probabilities, that is probability of P and probability of W. Okay. So that is to say, in a sense, it's something like saying that the word P appears in many contexts, like can appear in many contexts. The word W also may appear in many other contexts. The question is, what we are trying to measure is, that is, can we say that whenever one of them appears, the other one also appears? That kind of thing we are trying to estimate here. So as we all know that, like, if when we consider any two random variables A and B, right? Now we know that if A and B are independent of each other, then the joint distribution of A and B is equal to P of A times P of B, right? So here, if these two variables were, I mean, these two words were independent of each other, then this thing should really be somewhere close to 1. Okay, if this were close to 1, that would mean that that is they usually are independent of each other. There is no real relation between P appearing to P and W. That is, we cannot say that whenever one appears, the other also appears, or something like that. Okay. But so the, like, if this is nearly equal to 1, that is, these are quantities which we can estimate from a very large data set. Like we have already discussed how to estimate probabilities from a large data set, like an annotated data set like this. I mean, in this case, of course, you do not even need any annotation. You just need the context. You already know the word P, already know the word W. You are just checking whether they appear in each other's context or not. So accordingly, you can like just calculate this thing. So this is like called the mutual information. So based on this quantity, you are like, it's possible to induce the that is some kind of a score. And so this I am doing for the positive things, I mean positive word. A similar thing, that is the similar mutual information, I will also calculate for with negative words. Okay, and not for a single positive word, I will do it for all positive words. Similarly, I will do it for all the negative words also. And as a result, what will happen is that I will get a sense of whether this word W tends to co-occur with positive words, or tends to co-occur with negative words, or or neither of them is true. I mean, it seems to be independent of both positive words and negative words. So that is to say, if it turns out that this usually goes with positive words, and less it's less likely to appear in the context of a negative word, then we that is accordingly, this word W will be induced a slight positive polarity. On the other hand, if I find that this word W tends to co-occur or more in the context of negative words than positive words, in that case we may give it a small negative polarity. Now, what exactly will be the amount of the, I mean, the score of this, I mean, the P score in this case or the N score in this case, that of course depends on which specific algorithm which that you are using. I am not going into any specific algorithm. I'm just giving the idea. So this is basically the way in which you expand your Senti word net by initially building a set of anchor positive words and anchor negative words, and then using these concepts of co-occurrence to induce the P scores and N scores of the other words which are neither anchor positive nor anchor negative. This way the different and this is like a, it's a you can say that this is an iterative process. So initially your anchor words were just this, and the like you had let's say capital P number of positive anchor words and capital N number of negative anchor words. Okay. So the way this proceeds is the process of building SentiWordNet proceeds is as follows. So let's say that this is like basically the set of all words. So now what you do, and you have initially these P positive anchor words and N the negative anchor words. Now what you do is you like as I said earlier, you take any random word W, you calculate its mutual information with the positive words, calculate its mutual information with the negative words. Based on that, you make a decision whether this word tends to co-occur more with positive words or more with the negative words or neither. Now suppose this you find that this word W tends to co-occur a bit with the positive words. Then what happens is a positive sentiment is induced with this word. So you can like expand your positive word set by taking this W into it. Okay, so this W gets added to the P set. Your P set grows a little bit. Next you take another word, let's say V. Again you now when you are comparing its this you are calculating its mutual information with the different words in P. Now you are including this W also, since W has already been added in P. So again you do that same test, and suppose this time you find that V has a slight co-occurrence chance with the negative words. So you attach some N score to V and you expand N by including V to it. Okay, and this way you keep like again you will take one more word, let us say U. Again you will do the same test. Let's say this U also is found to be to have a slight bias towards N. So again you will grow N further and to bring U in. Okay, so gradually this way what keeps on happening is that you keep on expanding both the P sets and the N set. At every step you bring in a new word, assign it to any of one of them, and assign it a P score or an N score depending on wherever you added it. And like as you try to grow them further, these new words are now again being used as anchors. Okay, so this is so like it's an you can say this is some kind of an iterative process. You may repeat this for some k number of iterations. Now this k may be either like a fixed quantity, or you may continue doing this till you have like exhausted all the words in the vocabulary. But so one thing to be noted is that as you are like going further and further, then that is as you are going into a higher number of iteration, the scores which you add to the you attach to these newly acquired words, those scores will have to keep on decreasing. That is, this word W, note that this word W initially is neither a positive anchor word nor a negative anchor word. That is, it does not have any P score or N score to begin with. Okay, now you find that W tends to co-occur with some positive word. So you give it some positive polarity. Okay. But it is not a positive, but mind it, W is not a positive word. It only tends to co-occur with some positive word. So you cannot give it full like a positive P score of 1. You can give it a P score maybe of half. okay, or some other value, but definitely not 1. Next, you suppose after W, the next word to be added to the P set is something like X. X is another word. Now, remember that earlier you did not add X. That is when you are considering only the original set, you had probably not added X because you could not like relate X to any of the words which are originally existing in P, any of the anchor words. X did not co-occur with them, but maybe X co-occurs with W. Okay, but so X does not co-occur with any of the positive anchor words, but X does co-occur with W, which in turn it has a tendency of co-occurring with positive words. So in that case, the P score you will attach to X has got to be even less than the P score of W, right? So if W was 0.5, maybe the X will have a P score of 0.25 and so on and so forth. Okay, so this way you keep on expanding your senti-word net by bringing in more words. But as you are doing it, you have to keep in mind that the P score and N scores which you are associating with them, they also must keep reducing. Okay. So this is basically the story of how the senti-word net grows. Now, as I was telling earlier, now given up a particular sentence, what you need to do is you have to like assign the different words to you have to assign sentiments to the different words that are of interest. So as we are saying, consider the example which we had discussed yesterday, say customer reviews of a product. So we considered this kind of we considered basically a sentence like say picture quality is great, but battery life is not so good. This is what we considered yesterday. So using the concepts such as word sense disambiguation and so on, we had found that let's say we have already found that picture quality and battery life, these are the target words. I mean, these are the aspects of the product whose with which we are trying to measure what sentiment has been attached to them. And we find in their context, we find that this word great is there, which of course has a high P score of 1. Okay, so that P score gets induced onto this. So we take a we can understand that picture quality, this aspect has got a high score +1. Now for in case of battery life, we again search its context, we consider its context. Within the context we find one sentiment word which is a good, right? And which is of course another +1 word, that is it has a P score of 1. Okay, but we find that between that and this there is also the word not, right? So this is what is this? This is a negating word, that is the sentiment is inverted. So what was +1 now becomes -1. So we make this as -1. So for battery life, the sentiment polarity becomes -1 and so on. Now the problem is that we cannot, the structure of sentences can often be quite complicated, and when people are expressing a sentiment, they may not do it in a straightforward way. They may do it in a roundabout way through analogies or comparisons, or using word or using some language which does not actually use any well-known sentiment word and so on, right? So having a simple rule like this, that is you found a negating word between the between the sentiment word and the target, so you just invert the sentiment. This does not often work, especially when we have long and complex sentences, right? So what is really needed is like like a more complex representation of a sentence. So if we can somehow represent a sentence, like if suppose we have a sentence and we can represent that sentence as a vector. Okay, suppose the sentence somehow became a vector like this, and then you could take, then what you could do is you could train a machine learning algorithm. You could take lots of sentences which are either expressing a positive sentiment or expressing a negative sentiment. So you basically reduce it to a classification problem. You will have a sentence which is represented like as a vector, instead of yeah, let's call it like this, which is represented as a vector, and the correspond instead of w, let me write it as x. So this x is a sentence, and along with x there exists y, which is the sentiment level. Okay, so basically why am I doing this? I am doing this because that is given a sentence, it is not like always straightforward to I understand what is the sentiment that is being expressed. It can the sentiment can be expressed in a subtle way or through like a more complex set of language, etc., which is difficult to encode through a single rule. So so that is why what the claim is, or the idea is, that let us represent the sentence somehow as a d-dimensional vector, and corresponding to that d-dimensional vector we will have the label. And then what we will do is we will learn a function f, which basically takes a sentence, any sentence x, and maps it to a sentiment score, I mean sentiment level. That is either positive, this is a positive sentence, or this is a negative sentence, or this is a neutral sentence. Okay, so this is what needs to be done. So what is this function f? This function f can be like, it's basically some machine learning algorithm, right? So we have already discussed some machine learning algorithms earlier, say for example decision tree, or maybe Bayes classifier, right? Apart from that, of course, we had also discussed about neural networks. So we know there are machine learning algorithms. So what any machine learning algorithm does is it takes a feature vector from the feature space and maps it to the label space. In this case, the feature vectors are nothing but the sentences which are somehow expressed as a d-dimensional vector, and then expressed and then mapped to a sentiment score, which is like either p or n or neutral. Okay, so once if I am able to represent any sentence as a d-dimensional vector, and once I have a large enough corpus of these sentences labeled with sentiment, then the rest of the things can happen directly by using any of the self machine learning algorithm that you want. The challenge is how to represent a sentence as a vector. Okay, so that is the central challenge. How to represent a sentence as a vector. So before say, and also another so like you may be tempted to say something like this, that we know that every sentence is a sequence of word tokens. So why not do this? Every word token maps to every word, like one word in the vocabulary. So that is like, suppose I have that is there is a sentence whose the door was open. So why don't I do this? I go to every word, check what is its like number, or what is its index in the vocabulary, and just create a vector out of this. Let's say the word the, its index is 1. the word door, for that the index is 59. For walls the index is 27, and for open the word is the index is 93. So based on that I make a vector like this: 1, 59, 27, 93. So this is something which you may be you may be interested in doing, or it may appear as a natural solution, but it has very serious problems. So what is a serious problem? The serious problem is that in for any machine learning algorithm, the feature vectors have to be of the same size. That is, this dimensionality d has to be common, has to be fixed for all the inputs. But the way we have defined it here, d is nothing but the number of words of the sentence, the length of the sentence. But different sentences of course have variable lengths. So we cannot have this is a 4-dimensional feature vector. I cannot write a 12 word sentence and then have a 12-dimensional feature vector along with it. That's not possible, right? No machine learning algorithm is going to allow that. So this is not a good approach. This cannot be done. Also, this is not a good approach for another reason also. It's because it's too rigid. You are basically there is all the words that are present in the sentence. You are basically localizing them to a particular position in this feature vector. That is, the first word is present in like it is the first word, the first index of the first dimension. The second word is the second dimension, third word is the third dimension, and so on. So now suppose if I am comparing this sentence with another sentence which have roughly the same meaning, then unless that is I will not be able to understand that this vector and the vector corresponding to that other sentence which means the same thing, I will not be able to link them unless they are the words of both sentences are aligned like that, which will probably not happen, right? So that is why this is not a good idea. So then what to do? So that is so if d is not the length of the sentence, then what else can it be? The answer lies in this whole technique of word embedding, which has become one of the most important and the most state-of-the-art technology in natural language processing. So what is word embedding? So as the name suggests, it says that represent each word token as or each word as a vector, and that too as a d-dimensional vector. Now what is d? So like d is any value which the user wants. Okay, so now what we are going to now briefly discuss is how to do this word embedding. That is how to represent a word as a d-dimensional vector. Okay. So so there are very well-known algorithms which do that. We will not go into details of any algorithm, but first of all let's just try to understand why at all I want to represent or what may happen if I represent a word as a vector. Okay, so so one simple way in which I may want to represent a word as a vector is as follows. So suppose I have my vocabulary size is v. Okay, so let me build a v cross v matrix like this. So every word here, like every row stands for each word in the vocabulary, every column also stands for every word in the vocabulary. Okay, so W1, W2, all the way up to WV along the rows, and also W1, W2 up to WV along the columns. Okay. Now consider what does this matrix contain? Let me, I'm calling this matrix as C. Now consider the ijth entry of this matrix, Cij. Okay, so the row corresponding to it is of course about the word wi, and the column corresponding column is for word wj, right? So then Cij in a sense is that is it's a sense of the co-occurrence of the words wi and wj. It's like saying that whenever or how many times these two words appear together within the same context. That is to say, what do I mean by that? That suppose the word wi appears somewhere in a document, then I must consider as neighborhood m of it and see if wj occurs within it or not. Okay, so basically I will start like I will track every occurrence of the word wi and check whether wj is appearing somewhere close to it or not. Yes, the score I will get that way. I will put it as cij. Now if I want, I may also normalize it by something like this. Okay, it's this. So this basically saying that whenever wi, the word wi occurs, how often is it accompanied by wj also? So this way also I can define it. If I define it this way, then cij is equal to this, and cji will of course be just the other thing, that is number of their co-occurrences divided by number of occurrence of wj. That is, whenever wj occurs, how many times is it, or what fraction of the times it is also associated with wi. So this way I can get what is known as a co-location matrix, okay, or co-occurrence matrix. Okay, so so obviously this is a v cross v matrix. So now if you consider any particular word, let us say or like if you consider any particular column W2, what information this column is carrying is basically this word W2, how often it co-occurs with W1, how often it co-occurs with W3, how often it co-occurs with W4, how often it co-occurs with WV. So all like this kind of a vector I will get. Okay, and this is actually a powerful representation because we know that if a word occurs quite often with another word, then semantically there must be some kind of connection between those two words, right? That is like if I come across the word say bat, and I find that then I may expect that word to co-occur with such words such as ball, stamp, maybe also ultrasonic sound in case we are talking about the animal called bat, night, etc, etc. So these are some like various words with which it will co-occur. Okay, so in a sense this kind of a co-occurrence or collocation vector, it is indicative of the sense or the meaning of the word which we are, or rather the meanings, the multiple meanings of the word which we are considering. So this is one possible way in which you can represent a word by a vector. Okay. The problem with this approach, of course, is that the vector length is very large, V. So like in general, V is what? The V is the vocabulary size. So in general, that can be quite extremely large. It can be say a few million words. So I do not really want to represent my words as a million dimensional vector. Why? Because computation will be difficult. That is, I don't really want a like a this a million dimensional vector to be fed into any classification algorithm and so on. Okay, so that is why what we have to do is we have to utilize algorithms such as glove or word to wake. So these are also algorithms which are based on the concept of co-occurrence. Based on co-occurrence and based on probability. Okay. Why probability? So let us say so let us consider any two words wi and wj, which are appearing in the context of each other. Okay. Now, now what happens in these kinds of algorithms is that they try to predict a score. Okay, that is when that is you have let's say you focus on the word wi, and you try to like estimate a probability of what its surrounding words can be, right? So like for example, you like again coming back to the previous example, if this the word wi, if the target word is bat, then you are basically trying to guess what its surrounding words can be. Of course, like we do not know, so like the different words will have different probabilities. Say for example, this vector itself, it carries some information like this, right? So now what happens in these algorithms is that, look at the following document here. Let us say that uh, I have let us say that I have a like I have a matrix U and another matrix V. Okay, now from where these matrices came from, as of now, don't ask. Let's say that they are somehow there. Now what is happening in this case is that, so suppose x like that is you have a particular word which you are calling as let's say you have a sentence, you are focusing on the cth word, the word which is in position c in that sentence. Let's denote that as xc, and then you consider the context of length m on both sides, that is from xc minus m to xc minus 1 on one side, and xc plus 1 to xc plus m on the other side. So these are basically the context words. In between here, of course, the word xc is sitting. Okay. Now what we do is we basically we generate the one hot vector of one hot encoding vector of this thing. So we know what you mean by one hot vector. So you basically each of these word tokens are to be represented by a v-dimensional vector, where so if this word token is associated with the kth word in the vocabulary, then the kth position will be 1. All the other things, all the other positions, v minus 1 positions will be 0. So this is what is known as the one hot encoding. So for every so for each of the words in the context, I will simply create a like a one hot encoded vector like this. So there are 2m number of context words, m on this side and m on this side. For each of them, I will get their corresponding one hot encoding. Now what I will do is I will multiply each of them by this matrix V. So again, let's say this V is a D cross V matrix. So remember that these are all V dimensional vectors, where V is the vocabulary size, and this matrix V, this curly V, this is a D cross V matrix. Where what is D? D is basically the dimensionality of word representation which we want. Yeah, so like what based on how much ever computing power I have, I will choose D. I mean, D should not be, if D is too small, then I will probably not be able to express the different kinds of words. But not do I want D to be extremely large, say in the order of millions or something. So I like, let's say I make a compromise and choose D equal to 100 or something like that. So what I do is I carry out this vector multiplication. These are like the one hot encoded vectors. They are multi or left multiplied by this matrix. Then what happens is that now the vectors I get after the multiplication, I simply take an average of them. So there are 2m such vectors corresponding to the 2m context words. I take their average. Now what I do is I generate a score vector like this. Now this so remember that this is a d-dimensional vector. So this V is D cross V, and each of these are the X. These were all V dimensional vectors. So after the matrix multiplication, we got D dimensional vectors. I mean, here it's written as N. So N is it's N or D. That's basically the dimensionality of the word representation which you want. So once you get that, then what you do is you generate a score vector like this. That is, you have another matrix called U, and and it's like V cross D. Okay, just like this V matrix, this was D cross V. Similarly, U matrix is V cross D. So you can again pre-multiply it with, so you get V cross D, you multiply it with the D dimensional vector theta, and you get back another V dimensional vector Z. Okay, so now this vector, this is basically something like a score vector. It's basically giving you the probability of, so remember what is V? V is the vocabulary size, and what this score vector is giving you is basically the probability that each of the words in your vocabulary will appear in the context which we are considering. That is, remember that the target word is XC, which we have kept aside, and these are all the context words. Now, using the context word, I am basically estimating this Z, which is a score indicating what is the probability of uh, occurrence of every word in the vocabulary within the context of this target word XC. Okay, so so this Z I will is in general, it will not be a probability distribution, but I will convert it into a probability distribution by applying the softmax function. So softmax function is like it's a function which takes any vector as input and converts it into a like a probability distribution of the same dimension. That is, in this case, this Z is a V dimensional vector. This if I apply softmax to it, I will basically get a probability over V like V items. So it's like I will get a probability that the first word W1 in my vocabulary, what is the probability that it appears in the context of the target word. Similarly, W2, the next word in the vocabulary, what's the probability that it appears in the context, and so on. So that way, what I will get is I will get like I will get an estimate of the probabilities of all the V words in my vocabulary. Probability of what? Probability that it appears or it may appear in the context of the target word which we are considering XC. Now, the thing is, we already know what words are the context of XC. That is, these words which we are considering, XC minus M, XC minus M plus 1, or XC minus 1, XC plus 1, XC plus M. We already know these words. And we also know that they are appearing in the context. So now that we have calculated, that is, we have got an estimate of these probabilities, I will be interested to to calculate what is the probability that this word appears in the context of XC, the target word. What is the probability that this word appears in the context of XC? What's the probability that this word appears in the context of XC, and so on. So all these values I want to calculate, and that I can calculate that easily. So, but remember that these probabilities which I have got here, that is the probability of any arbitrary word being appearing in the context of the target word, that those probabilities are dependent on U and on the matrices V and U. So remember, just note how we calculated the probabilities. I first took all the context vectors, multiplied them by V, took their average, then applied, then multiplied that average by U, and so on. And then only I applied the softmax function. Okay, so clearly U and V, these two matrices are playing a role behind this kind of assigning these probabilities. Okay, so now, but remember that I have not specified how I got U and V. In fact, I have not got them so far. I am only modeling the process in this way. So now what I am going to say is that I will choose U and V in such a way that this probability is maximized. Why do I want to maximize this probability? Because this is an event which has already happened. I already know that these words are appearing in the context of XC, the target word. Now, if since this is actually happening, it better have a high probability according to my model, because as we know that only things which have a high probability, those only happen. That is, we do not really expect something which has a low probability to happen, right? So since this has happened, I mean, since these words have appeared in the context of the target word, they better have high probability of appearing. So what we do is we choose U and V in such a way as to maximize this probability. Now, how exactly that is done, I will not go into that, so that requires quite a bit of advanced mathematics. But this is the broad idea. So, so this is basically the problem which they have to solve. It's like choose U and V in such a way that a probability like this is maximized. Okay, and so now once you have got U and V, so remember that V is basically a D cross N, D cross V vector, right? Where what is V is like the vocabulary size, and what is D is the dimensionality of the word vector which you want. So basically you can consider the matrix V to be something like this. It's like or if you want, sorry, the word you may appear to like this. So it's a V cross D matrix, right? V this way and D this way. So yeah, so it's like saying that for every word v, so it's like saying that for every word v1 you have a d-dimensional vector like this. For v2 again you have another d-dimensional vector like this, and so on. So basically what you have got this way is basically you have got a vector representation of every word in the vocabulary, and based on what? Based on co-occurrences. That is, the entire idea was to choose the U and V in such a way as so as to maximize the likelihood of the of this word having a particular context. So based on this notion of or concept of context, we are able to get some represent each of the words by some d-dimensional vector. So in this case also we had done the same thing, but in this case basically I got a v-dimensional vector which is very high. So here what I am doing is I am that is with the by cleverly using the concept of matrix multiplication and by defining probabilities of co-occurrence in a clever way. What I could do is, instead of having a v-dimensional representation of every word, I now get a d-dimensional representation of any word, where d is my like it's a value in my hand. I can choose if I want 100, so it will be 100. So this way what happens is that every word gets represented by a vector. Okay, each word represented by a vector. So obviously this this process has to be done over a very large corpus. That is when we are calculating these contexts, it cannot be just based on a single sentence. It will have to be based on a very large number of sentences. Okay, and so which of course requires a very large corpus. But at the end of the whole thing, I will get an get an U and V matrix, based on which I will get a d-dimensional representation of every word. Okay, now So these kind of vector representation of words, they have certain properties. So it's like saying that if two words are quite similar to each other in so let us say good and great. Okay, so these two words are more or less similar to each other. So it means that their corresponding word vectors will also be similar to each other. Now, what is meant by two vectors being similar to each other? It can mean many things. It can it can mean something like their cosine similarity is the same. Now you know what is the cosine similarity of two vectors. So let us say that the word good is represented by vector u and the word great is represented by the vector v. Both are d-dimensional vectors. So I expect that u and v will be close to each other, which basically means that their cosine similarity, which is calculated in the in the following way: u transpose v, that is the dot product divided by the magnitude of u times the magnitude of v. Right? So this is called the cosine similarity of u and v vectors, and it's in a sense it's something like if you consider the two dimensions, then we know that maybe this is the u vector, and maybe uh, this is the v vector, right? That is, we are by cosine similarity, what we really mean is the cosine of the angle between them. So it's telling us that whenever two words have roughly the same meaning, that means what? That it will co-occur in the context of similar words, or they will tend to have similar words as context. So as a result of that, what will happen is that their corresponding embedding vectors will be quite close to each other. And it's also interesting to, like, various interesting games can be played using these word vectors. So suppose I give you a sequence like this: France, Paris, India. Okay, and now you are required to predict the fourth word. Okay, so and if you if we look at this, like most of us will easily say the answer is the fourth word will have to be New Delhi. Why? Because like we first said France, and then I mentioned the capital of France, then I mentioned India, and so now I must be mentioning the capital of India, right? So now like people have actually carried out an experiment to see that suppose the word France is represented by vector v1, which is a d-dimensional vector. The word Paris is represented by v2, which is another d-dimensional vector, and the word India is represented by v3. Now suppose I carry out v1 minus v2 plus v3. Okay, sorry, that's not right. Suppose I like basically what I so let's say that this fourth word is, which I am looking for, is an unknown word v. Okay, an unknown word v. So basically what do I want? I want v1 minus v2 should be nearly equal to v3 minus v. Okay, so suppose so like if this equality held, then I could have calculated v as follows: v is equal to v3 minus v1 plus v2, right? That just follows from the normal algebra. So if now I know the vectors v3, I know the vector v1, and I know the vector v2, so I can just subtract and add them. Okay, and that way I will get a vector v. Now, if you try to map back which word this vector v corresponds to or nearly corresponds to, so every word has its corresponding vector representation. Now you have got this vector v, which is a new vector. Now you are trying to find which word this v is closest to, and you will find that the word which this V is closest to is actually New Delhi. So people have played these kinds of games using word these word embeddings and have actually found it and actually have come to be quite successful. Now that we know how to do word embedding, that is we are able to represent a word as a vector, now you come back to the concept of sentence embedding. So sentence, as we know, is nothing but a sequence of word tokens. Say W1, W5, W37, W23, W127, W4. Let's say this is one particular sentence and these are the word tokens that are present in the sentence. Okay, and also let us say that this sentence is associated with a sentiment Y. So what should I now do? I will basically have to, and now this W1, each of these words I know their vector representation. The word W1 is represented by vector V1, which is a d-dimensional vector. Similarly, the word W5 is represented by V5. This is by V37, etc., etc. So once I have got all these vector representations of the individual words, now I will have to make a vector representation of the whole sentence. So now you may be tempted to think something like, why don't I do this? V1 plus V5 plus V37 all the way up to plus V4. I basically add them up and maybe divide by the length of the sentence. Basically, I take an average of all the word embeddings and use it as the sentence representation. Now, it's not that this is wrong. It is something which people have tried, but they will get a limited amount of accuracy. Okay, but for a higher accuracy, what you can really do is you can feed this whole sentence to an RNN or an LSTM. So we are already familiar with the concepts of RNN and LSTM. We already know what they do when we studied the time series. So in this case, it's like both RNN, LST and LSTM, they're taking a sequence as its input. So this sequence which we are talking about in this case is the sequence of word embeddings. At every point, that is that let's say whichever, suppose we are using an RNN, so it has an hidden state. Let's call it as H0 initially. Then I put V1 to it. So the first word vector. So then the hidden state changes to H1. Okay. Now I put the next word to it, which is V5, and the hidden state now changes to H2. Now I put the next word, which is V37, and the hidden state changes to H3. Similarly, finally I have H7, which is the hidden state after all the different word tokens have been put in, or the words have been put into the RNN one after another. So what is this H7? H7 is it's a you can say that this is what we get is the hidden state of the RNN or LSTM. It's basically an intermediate representation of the sentence. Now, what is the size of this representation? So that we do not know. Depends on what what is the exact size of your hidden variables. So that depends on the architecture of the neural network. Whatever it is, this H7 that is the hidden layers at the end of or after feeding the full sentence, that represents the intermediate representation of the sentence. So just for the sake of it, let us say that this is a RP. That is, it's a p-dimensional vector. I mean, I'm not saying that this is what it should be. This is what it can be. It can be something. It need not even be a vector. It can be a matrix or something higher dimensional also. So then what happens is that this whole sentence you have replaced by this H7 which is a p-dimensional vector, and along with it you have the sentiment y. Okay, so basically what you now need to do is you need to learn this machine learning algorithm F, which like learns to take a p-dimensional sentence embedding vector and map it to y, which is a sentiment level. Okay, so now again which ML algo you will use is up to you. So this is something which you can do. Okay, so this is the way basically in which sentiment, in a nutshell, this is the way in which sentiment analysis of is done. I mean, sentiment analysis of a sentence is done using the deep learning. So so if we have to do the sentiment analysis for the economics problem, that is especially for example for the customer review problem which we talked about, that is we need to identify the different aspects of the product which the people are talking about, and we have to identify the sentiments which they have expressed about each of those aspects. So for that, what we need to do, the first step is you have the customer review, you break it up into parts where every part corresponds to one particular aspect of the product. So how do you do that kind of thing? With the help of word sense disambiguation and other things. Now once you have identified the like these small parts of the review, where each small part, maybe a sentence, is about a particular feature or a particular aspect of the product, then what you do is you feed that sentence into a this kind of a classifier which has already been trained on a like a large corpora, and which basically takes in a sentiment and is able to predict whether it's I mean, it takes in as a sentence as its input, and it predicts the sentiment associated with the sentence. So similarly, that's the same thing will be done in your case also. That is, you will feed that is, you have the sentence which is talking about a particular feature. Let's say the battery life of your camera. You feed that a sentence to your to the trained RNN model. For that, of course, you need to estimate, like express each words or each word token in the sentence using its word embedding. That is, your sentence will now become a sequence of these d-dimensional embedding vectors. So that vector that sequence of vectors you will feed to your RNN or LSTM algorithm, and it will give the sentiment as the output. Okay, so basically this is how sentiment analysis works, and you can use it in the context of economics. Okay. So basically with that we come to the end of this topic as well as of this course. So as I already mentioned earlier also, that on the coming Monday, which is I guess 15th, same time 5 to 6, you will have a